So, this is part 2 of the stress transformation video. This is where we left off last time with our matrix of stresses and our 3D stress block and 2D stress block. So what we want to do is to put that on the Mohr's circle, and we're going to interested in finding our principal stresses, our max shear stresses, and their corresponding angles, and we're also interested in rotating this stress block 25 degrees clockwise and finding the stresses on that. So we'll start by just finding the coordinates of our Mohr's circle. So for our x-coordinate, our first term is always just what is in the normal stress in that direction. So in this case, it's our positive sigma xx. So that's just going to be 0.4 megapascals. And then our second term is our shear stress along the x face. And since that is causing a rotation that is counterclockwise, that means it's going to be a negative 0.057. So we do the same thing for the y-axis. That's going to be 0 for it, since it doesn't have any normal stresses acting on it. And it has a positive 0.057. So now we just have to plot these on our Mohr's circle. So here is the stress, or the Mohr's circle for our stress block that we currently have. We've just plotted our x and y, and I drew a line connecting the two, and so now the first thing we want to do is find out exactly where the center of our circle is going to be, and so the center is just calculated by taking the sum of the kind of x coordinates, which for both of our x and y coordinates, so it's 0 plus 0.4, and all of that divided by 2. So that gives us the location of our center, and so that's going to be at 0.2 MPa is where our center is. Now the next thing we want to find is we want to find our radius, which we can just find by taking the square root of our center, which is 0.2, which we just found, squared plus 0.057 squared, which is the height of our triangle. Take the square root of that, and that'll get you 0.208 MPa. So our triangle in this case is, you can kind of see, is going to be right here. That's our triangle that we're kind of looking at. And so that's going to be our R, and this is going to be our center. Now that we have those two variables, we can go ahead and find what our principal stresses are, which is our sigma max and sigma min. So sigma max in this case is just going to be whatever our center is, 0.2, plus the radius, 0.208. So that's going to give us a value of 0.408 MPa. And similarly for our sigma min, another principal stress, is just going to be the same thing, our center, but instead it's going to be minus our radius, 0.208. So that's just going to give us a value of a negative 0.08 megapascals. So those are our principal stresses, and then also if we wanted to find our max stress, tau max, that is just going to be equal to our radius, which is going to be 0.208 megapascals. Next up is to find the angles at which these principal stresses and max shear stress occur. So if we focus on first the principal stresses, that angle, that's going to be what it takes to rotate our red line, rotate it to the axis right there. So that is going to be called our 2 theta p. So remember, on a Mohr's circle, a certain angle is actually actually half as much as it would be in like the real world. So that's why it's 2 theta p rather than just theta p. So in order to find what our theta p is, we need to figure out what that theta is, in the pink theta that I have there. And so I'll just draw it on here right now. So we also need to find what the angle is to get our max shear stress. And so that's just going to be the angle it takes to rotate all the way to that point. So that's going to be our 2 theta s. So first let's start off by finding out what our theta is, just that angle, not the 2 theta p, but just the angle by itself. So that's just going to be equal, if we use our triangle again, that's going to be equal to the inverse tangent of our height of our triangle, which is 0.057, times like the width of the triangle, which is our center, 0.2. So that's going to give us an angle of 15.9 degrees. So now we just need to relate this angle to both our 2 theta s and our 2 theta p. So the easiest one will be for 2 theta p. So 2 theta p, that's just going to be equal to whatever our theta is. So that means that our theta p is just going to be equal to a 7.95 degrees going counterclockwise. So now for to figure out our 2 theta s, that's just going to be equal to 90 degrees plus whatever theta we get. So when you do that, you get that theta s is going to be equal to 52.95 degrees, also going counterclockwise. You can also find each of these angles has a complementary angle if you twist in the other direction. But for this case, we're just going to keep it simple and use these two. So now let's draw these on the rotated stress block and put the stresses on. So here is what those angles and corresponding stresses look on a 2D stress block for both cases. So on the left one we have our principal stress case where it's rotated 7.95 degrees counterclockwise, and we got our two principal stresses, our minimum and our maximum. And then on the right one we have it's rotated 52.95 to get the max shear stress of 0.208 megapascals, and then we have a constant axial force along the outside, which is what our center is. So those coordinates work out. And then you can see we have our rotated axes for our y prime and x prime based off of how much we rotate the stress block. So now the last thing we just got to do is we want to find the stresses. Find the stresses for a 25-degree clockwise rotated stress block. So if we draw that on our Moore's circle, that's basically, it's going to look something right about here and here. If we draw that line through our center, oh, got that a little wrong. Okay, so this is going to be our y prime and our x prime. So we're basically rotating counterclockwise 50 degrees. So on our Moore's circle, it's going to be twice as much as it's rotating in real life. So that's going to be 50 degrees rotated. So we're trying to find the stress block for this new x prime, y prime. So in order to do that, we kind of just need to make a triangle and kind of solve it from there. So our triangle in this case, for this new y prime that we kind of have, it's going to be kind of look like this. So this is the triangle we're interested in. So if we take that and draw it down here, and we'll take our new triangle. So that's basically the triangle we're trying to solve. So we're going to have some length 1 and another length 2, and then this is going to be our radius, which we already know. So we need to go ahead and find this angle. So this angle right here is going to be equal, so we'll call that theta 1. So theta 1 is just going to be equal to our 50 degrees that we rotated, and then you can kind of see we have a little bit of an angle from our initial angle, which is going to be equal to our theta, which we already calculated. So that's going to be plus our pink theta, which ends up being 15.9 degrees. So that means that we know what this theta 1 is going to be, so that's just going to be equal to 65.9 degrees. So now we can go ahead and solve for what our lengths are. So since we know that the sine of 65.9 degrees is just going to be equal to our L2 over our radius, that means we can solve for L2, which is going to be equal to 0.19. We can do the same thing for solving for L1 using the cosine, and that'll get us an L1 that's equal to 0.085. So using these two lengths, we now can find what our new coordinates are going to be. So let's go ahead and start with our y prime coordinate. So our y prime coordinate, that's just going to be, so our first term is our term that is on our normal stresses, our sigma, so that's kind of like our x-axis. So that's just going to be equal to our center minus whatever our L1 was. And then our height, which is basically where our shear stress is just going to be our L2 term, because our L2 is just from the axis all the way to the point. So that, if you do that math, the center minus L1, that'll get you 0.115 and 0.19 MPa. So that's our coordinate for our y prime. And so our x prime coordinate, that is just going to be the center plus L1, and then we're going to have a negative L2, because now we're on the other side, the underside of the axis, if that makes sense. If we look back to our diagram, that can kind of make sense. Okay, we have our center plus whatever value that L1 was, because it's going to be symmetric on either side. So when we do that math, you should get that our x-coordinate is going to be 0.285, and then you also have a negative 0.19 MPa. So now all that's left is to put this on a stress block. And so this, if you put those coordinates on our little stress block here, this is what you'll get as a result. So now we have our rotated block 25 degrees clockwise. And so if you can use those coordinates, you look at both the y prime face and the x prime face, you'll be able to put those coordinates in the right directions. Basically the opposite of what we did to get the Mohr circle in the first place. So you just got to kind of go back and forth. So that is what our stress block looks like with those forces on it. And that's our final thing for this video.